In this last part of the first section of chapter 12, we're going to finish up our inference for linear regression. In the last part that we covered, we talked about linear regression, reminded you about linear regression, and also how we could start doing inference procedures on the slope, population slope, when we talked about how to do a confidence interval. But now we're going to talk about how to do a significance test or a hypothesis test on this population slope, or the true slope of the regression line. All right, so when the conditions are met, in the last part of this first section, we talked about how we could do a confidence interval and tried to estimate the population slope. Well, we remember we used the term beta to indicate the slope of the population. So we did confidence intervals to approximate what the true slope would be from our sample slope, from the least squares regression line. Using the sample data, we got a sample slope, and we use that as an estimate for the population slope beta. In this part, we're going to do significance testing. So we are going to test whether we think the true population slope beta is a particular value or not. So we're going to calculate a test statistic. It will be the usual format: statistic minus parameter divided by the square root of the statistic. By the standard deviation of the statistic. And I think we talked about it briefly in the last part, where this is going to be a t statistic. It ends up being a t statistic because the standard deviation of the statistic is not going to be known. We won't know the standard deviation of the population, so we're going to use the standard error, and as a result, we end up getting a t distribution. The difference here is that the degrees of freedom will be n, the sample size, minus 2. Okay, when we do our hypothesis, the null hypothesis will be that beta, the true population linear regression line's slope, beta, is going to be equal to some hypothesized value, quite often 0. The test statistic, like we just said in the last slide, is t. Again, it's t because we are dividing not by the standard deviation of the statistic, but the standard error of the statistic. The top is our usual statistic minus parameter. The statistic is our sample slope, the slope of the least squares regression line created from our sample data. And the parameter is going to be the hypothesized slope of the population. All right, we can have a one-sided test where the beta is going to be greater than some hypothesized value. It could be beta is less than some hypothesized value, or it could be a two-sided test where the alternative is that beta is not equal to some hypothesized value. All right. All right, so let's look at an example. Often we're going to not have to calculate things because they will give us a printout, a Minitab printout. You can see on this slide that I have a Minitab printout here, but I've covered up some of the information so that to force you to do some of the stuff yourself on your calculator. All right, so here's the example. Do customers who stay longer at a buffet give larger tips? Charlotte, statistics student who works at an Asian buffet, decided to investigate this question for her second semester project. While she was doing her job as a hostess, she obtained a random sample of receipts, which included the length of time in minutes the party was in the restaurant and the amount of the tip in dollars. Here are the data along with some outputs from a least squares regression analysis. So on the right here we have a table. Each row represents a table at the restaurant. The first number is the time in minutes that they were at the restaurant, and the second number is the amount of tip they left. for the restaurant. Okay, so we want to do some calculations. So first, what is the equation of the least squares regression line for predicting tip from the amount of time spent at the buffet? Define your variables. All right, so we are going to put those values, the time values, into the x, into the list one. Those will be our x, our explanatory variables. The tip will be the response variables. We'll put that into list two, and then we'll do a least squares regression analysis on our calculators, and it will give us this predicted tip in dollars, and then time in minutes will be our x. So remember too that if you use y hat and x, you need to define what those are. In this case, I used words to describe the variable, so I don't need to. All right, interpret the slope of the least squares regression line. All right, so the slope is the 0.03, and so that means that for every increase in 1 minute spent in the restaurant, the regression line predicts a tip to increase by about 3 cents. All right, so you can see that agrees with the Minitab printout. I revealed some of the Minitab printout now. I still have covered up part of it so that you can do this, the rest of this problem without looking at that and figuring out what the answers are by looking at the Minitab printout. So here we go, part C. Do these data provide convincing evidence of a positive linear relationship between the amount of time and the amount of tip for customers at this Asian buffet? All right, so this is a 4-step process. Think about what the state will be. All right, so the null hypothesis and alternative hypothesis is that beta is equal to 0, and that if there is a positive linear relationship, like the question's asking, that means the alternative should be that beta is greater than 0. And then again, of course, we have to say what beta is. Beta is the slope of the true regression line relating time at the restaurant and amount tip left. And again, always include your alpha of 0.05, because they didn't tell us what to use, so by default we'll use 0.05. All right, think about the plan. All right, the plan is the inference procedure we're using here is a t-test for slope, and then if the conditions are met. So now we got to look at those 5 conditions. Think first about the linear. All right, so we want to look at the scatter plot or the residual plot to see if the data is linear. So not a super strong, relationship. I think our r-squared would probably be pretty small. And actually, we can see at the Minitab printout up above that the r-squared is about 13%. So it means our r value is going to be pretty small. So it's a fairly weak linear relationship. But if we look at this residual plot, we can see there is no overall pattern in the residual plot, which indicates that a linear model is appropriate. Whether or not it's super linear is another thing. But yeah, a linear model's okay. It's weak, but a linear model's appropriate. All right, next thing we want to talk about is whether or not these are independent. Remember the acronym here is LINER, I guess, LINER. So the next thing we want to talk about is independent. So are these things independent? And so knowing one tip is not going to affect what the next tip will be. So like knowing one tip isn't going to influence what another tip would be. So probably safe to assume independence there. All right. The next thing we want to talk about is normality. and remember that this is really, I mean, theoretically, we want to make sure that for every possible input of the x value, all of the output y values would be normally distributed about the least squares regression predicted value. And we just don't have enough. Like, for example, very few, if any, of our inputs are repeated. So we don't really check this because it's almost impossible to ever really check this. So all we have to do really is look at all of the residuals together and make sure that all of the residuals are not horribly skewed. So we want to look at a histogram of the residuals or the normal probability plot of the residuals. Remember, if you're doing this by hand, your calculator saves the residuals. Once you've done the least squares regression analysis, saves all the residuals in that list called resids. So you should be able to pull those up and do a normal probability plot using resids, or do a histogram doing the resids. In both cases, these are appropriate. The residual, the normal probability plot of residual is fairly linear. The histogram of the residuals does not appear to be horribly skewed. So we're appropriate in both cases. Normality is okay. The next thing we want to talk about is equal standard deviations. So for that, we're going to look at the residual plot. So remember, this is the residuals plotted against all the x values. And so as the x values increase, there's not a horrible increase or decrease in the spread or how big or how small the residuals get. They do seem like they're getting a little bit smaller, but it's not awful. So in this case, we're going to say, yeah, it's about equal scatter about the zero line in the residual plot. And then the last thing we want to talk about is random. And yeah, all these receipts were random. Charlotte picked all of these receipts randomly. All right, so all the conditions are met. So now let's do the do. All right, so for the do, we know the degrees of freedom are 10. We can calculate our t statistic. The beta we can either get from the printout up above, or we get that the slope, not the beta, the slope, sorry, from our least squares regression line that we ran. The standard error is on the printout up above. I would think that we would probably give that in most cases. Calculating the standard error by hand is a little bit tricky. But you could do it. Remember, it's dealing with the standard deviation of the residuals and the standard deviation of the x values. So in that formula, that you could calculate it by hand. All right, and then we calculate our p-value. We do a t-CDF. We want to say what the lower value is, what the upper value is 1,000, degrees of freedom of 10, and that gives us a 0.1234. Notice that if we had been looking at the Minitab printout up above, that our p-value is exactly 1/2 of the p-value given in the Minitab printout. That's because the Minitab printout by default always gives us the resulting p-value, assuming we're doing a two-sided test. So our test is one-sided, so our p-value will always be 1/2 of what the Minitab printout gives. Now, the Minitab printout might not give us a double value if they say specifically in the Minitab printout that the test was a one-sided test. But if they don't tell you that it's a one-sided test, you have to assume by default it's a two-sided test. And so if our test is one-sided, we would cut their p-value in half, and it would then agree with ours that we calculated. All right, and then the conclusion, very similar to conclusions we've seen in the past. We compare the p-value to our alpha. So since our p-value of 0.12 is greater than our alpha of 0.05, we will fail to reject the null hypothesis. We do not have convincing evidence that the parties who stay longer at this Asian buffet leave larger tips. So we saw that the slope of our sample data was positive, but it wasn't very strong positive. And the relationship overall was not super linear because our R-squared value, I mean, it was linear, but it wasn't very strong. The strength of it was not very great because our R-squared value is pretty small. So our R value is pretty small. So, you know, maybe we could have gotten this value just by chance alone. And basically that's what's going on here. We rejected it. It's not strong evidence that the longer you stay, the more you tip. All right, so you have some homework. There are numbers 14 and 16, both have 4-step problems in them. 14 part C requires you to do a 4-step. I think in that one they're probably giving you the assumptions or giving you graphs so that you don't really have to check that. They're probably going to say, assume that the conditions are met. So you probably won't going to have to check all of 5 conditions in the plan part. In 16, you do have to. So you have 4 steps, and then you will also have to check and explain the 5 conditions. So make sure that you're doing that on number 16.